All right. The topic of today is conservation laws. And this is the part of electrodynamics where we start looking at stuff that's completely new to you. The stuff we've looked at before, like Poisson equation, charge conservation, diamagnetics, that stuff you've all heard of before at least. But from now on we'll start discussing theory that you probably haven't seen before. So I think it's more important than ever that you try to get a hold of the ideas, that you ask questions and are curious and try to figure out what's going on the blackboard. And if there's something that's not clear, you should stop and ask, because there's always more than one person who has the same question. Anyway, conservation laws are at the heart of physics, as you all know. I'm sure that you more than once thought that, well, this thing can't just disappear, so it's going to show up somewhere, and from that you're able to sort of figure out at least some properties of the system that you're interested in. And this is also the case in electrodynamics, of course. So what kind of conservation laws do we have in electrodynamics? Well, the most obvious one is charge, which we've discussed before. We also have conservation of energy, as always. And we're also going to discuss something that's maybe less obvious, but still is important, and that's the conservation of momentum. You might not have thought about it before, but light carries momentum. This is the principle of solar sails, for example. Okay, so I think we'll just start from the top and start by discussing charge conservation. And we've already seen the following. And that's the continuity equation. There you go. And we show that this follows directly from Maxwell equations. And we also show that this is equivalent to the conservation of charge. And we can show this just by applying the gradient to Ampere's law. And by integrating over a small test volume, we found that, let's see, if you balance the currents flowing out of the small volume by the total charge inside as a function of time, then we can show that this is equivalent to charge conservation. Okay? So we won't discuss that in much more detail because we already looked on it, unless there's someone who has a particular question about it. Okay, no one? Right, so next topic, energy conservation. In the same way as we looked at the conservation of charge, we might expect that if we have, let's say, a finite volume and there's some electrical fields, we know that they store energy. So you would also expect there's some sort of flow of energy out and some sort of local density of energy that would be somehow roughly equivalent to the current and charge density. And we're going to show a theorem which is central to the conservation of energy, and it's called Poynting's theorem. Okay, and we start off, as we did before, by considering a finite volume V. It might be a box, but it doesn't have to be. It's just some sort of arbitrary volume, but a box is easy to draw, so I'll pick that. And we expect some energy density inside the box, and some flow of energy in or out of the box if there's time dependence in our problem. And what this S vector is, we're going to get back to that, but for now it's just a flow of energy in some sense. And well, to get some hold of the equations here, we start off by looking at the Lorentz force law, because there we have forces and then we can relate work to forces, and work and energy is more or less the same thing. So a small amount of work can be looked upon as the force on, let's say, a small particle times the small length that the force acts on the particle. So let's say you're dragging a car along the street, for example, really heavy example. But now if we insert the Lorentz force in the F here, we'll get to electrodynamics right away. And now Q is the charge of the particle. And this is the fields acting on the particle. And let's see, I'll write it as v dot dt. So the particle is moving at velocity v for a short time interval t dt, giving a small length, and this is the force acting on the charged particle. Now, as you've noticed, there's a dot product here, meaning that, well, v cross b dot v again, well, that's 0, meaning magnetic fields do no work, as we've seen before. So this ends up being q v dot e dt. Right. And now I'll rephrase this a bit by noticing that if I have a charge distribution rho, I can write Q in the following way. It's the local charge densities times the small volume element. And I can write also rho times V, that's just a current. Like this. So first of all, I rewrite the Q as this. I take the rho, group it with a V, and voila, I have the current J. All right. So I get the following result. The power of the work being done is equal to the integral over the volume and E dot J. And, well, yeah. Now, J dot E is power density, and we can see that by looking at the units. And as we know, this is amperes per cubic meter. This is volts per meter. And, well, you know from basic circuit theory that current times a voltage is a power, meaning that we get watts per cubic meter, or power per volume. Okay. Yeah. And now, what does this represent? Well, it represents the conversion of electrical energy into mechanical energy, or the other way around. So if I'm moving a charge, I might expect that I'm changing mechanical energy into electromagnetic energy, and vice versa. If I let the fields move the charge, then I might convert out some of the electromagnetic energy into mechanical energy. So and let's say the direction of the conversion depends on the signs here, of course. Okay. Now I'm going to start manipulating this expression to get an expression containing only the fields. This means that I will get some sort of, yeah, that's exactly what I'm trying to do. I'll get get rid of the current and try to get only electrical and magnetical fields in there, because the currents are mechanical objects, right, moving around. So I'll try to convert the expression into fields, meaning it's a purely electromagnetic energy. So to compare the mechanical and the electromagnetic energies. Now let's see. If I start out by looking at the integral for the power, this one, And I'll convert the current using the Maxwell-Ampere law, or just Ampere's law. Let's see. Starting off with the expression for the power and expanding. Okay, and now we're going to need the following product rule, so I'll recap that. The gradient of a cross product can be restated as the following. There you go. And this is exactly the term I have up here, meaning I can insert this into here. And notice here that this is following. Let's see. This is just a time derivative of the magnetic field. This is simply Faraday's law. Now I can rearrange all this stuff and insert this term here. Up here. Okay? And if we now do that, we get that the integral is equal to let's see. All right, so when the dust settles, we see that there is some sort of magnetic field term, some sort of electric field term, and there is a vector, the divergence of a vector field here. And now we're going to have a look at these in, let's see, each of these. And we'll start off by this one. I'm going to try to reshape this term, and then I need a constitutive relation, as we've discussed before. And I'll just put it up here that for now we assume linear media, meaning that we assume a linear form for the constitutive relation, and we also assume isotropy and homogeneity of the media. So we're going to discuss this for now, the special case of linear media. All right, now if we assume the linear media and we inspect the following term, let's see. No, sorry, that was wrong. Let's see. No, sorry, it was right. I actually start off with what I'm going to try to prove. And if I set now E equals to 1 over epsilon d, as I wrote over there before, I get the following. This is now, let's see, a product rule. Because these ones are equal, I will get the same term twice. So it's 2 over epsilon. And then it's the d field times the time derivative of the d field. And, well, epsilon under the, well, d over epsilon. That's just the E field again. So I get back to this form. And this is exactly what we had in the integral, right? So I can take this one now, this term, and rewrite it as the time derivative of a dot product between the E field and the D field, which was essentially the, yeah, and there's a factor of 2. So if I divide over, you get back the electrostatic local energy density. Okay? And in a completely analogous fashion, we can look at the so-called magnetic term. Looks like this. And we can do the same thing, showing that this is exactly the time derivative of the local energy density. All right. So getting back to the integral again. First of all, we have the divergence of this vector, and now I'm going to define it. I'll call it S, and it's popularly known as the Poynting's vector. Let's see. We also had the energy density terms. I factor out the time derivative, and I get this is the electric field energy density, which is which, as it turns out, is the same as in electrostatics. And analogously, we get the magnetic energy density. And that's pretty much it. So it's the whole parenthesis here is now the local electromagnetic energy density, which I will call U, or sometimes the UEM, which is the electromagnetic local energy density. And let's see. Yeah, we define the Poynting's vector as E cross H. And because the integral now was over an arbitrary volume, I can reshape this into a differential law. But just let me clean this up first. So we get that the work on the charges, or from the electric field, or vice versa, is equal to the divergence of the Poynting's vector minus the time derivative of the local energy density, meaning that if energy somehow disappears from the volume, it has to convert into mechanical energy, or the electromagnetic energy has to move out in form of waves or some such. Let's see. D3R. U. I'll just call it U for now. If there's U without a subscript, I either did a mistake or it's the electromagnetic one. Okay, and since V was completely arbitrary, I didn't specify the shape or any other property of the volume. Then I can generalize this to a differential form. It looks like this. time derivative, the gradient, sorry, the divergence of the Poynting's vector, and work on the charges locally. And this is called Poynting's theorem. And when we define UEM, remember that we assumed linear media, which are isotropic. So if you run into media that don't have those properties, you'll have to look up a book or start from first principle and figure things out on your own. Now for the physical interpretation in more detail. First of all, the time derivative here. This is the time rate of change in electromagnetic energy stored locally in the fields. Okay, and this the gradient of the Poynting's vector. I say gradient all the time, but this is the divergence. Sorry about that. This is the flow of energy out of, well, if you think of this integrated over a small volume, it's easier. But then this is the rate of change of the energy inside the volume. Then this is the flow of energy out of the volume in well, electromagnetic energy. That's, well, you can see that because there's only the E and the H field, only electromagnetic fields in the Poynting's vector. Okay. Okay, and finally, there's this term, which is which makes this law different from the. Sorry. Yeah, there's a minus sign. Okay. This term makes this whole thing different from the charge conservation law because now it seems that there's some sort of source or sink. But this is actually just conversion into mechanical or conversion from mechanical energy. So again, it's the work of the electromagnetic fields on the charges or vice versa. Let's see if I can just continue here for a while. Let's see. Yeah, and this is essentially conservation of energy then, right? And yeah, the units of the S vector, to have that clarified. If you do all the unit math, then you find out that it's joules per meter square per time. So it's the flow of energy through a surface area, let's say through this table, if you have radio waves going through the table, and per time unit. And that's essentially power per area. So if you want to figure out how much energy a solar panel receives over, let's say, 1 hour, you just integrate the Poynting's vector of the radiation from the sun across a surface that's equivalent to your solar panel then. Okay. And if we set the time derivative of the work or the power, which disappeared from the blackboard, then we can, well, if you set that to be the mechanical power, we can note the following, and that's that the time derivative of the total energy density plus the divergence of the S vector, Poynting's vector, is vanishing. and that's energy conservation, which is more, well, this form is more closely related to the continuity equation, because it's on the same mathematical form. And, well, of course you realize that, let's see, time derivative of the mechanical energy density, that's just the current times the field. There would be a magnetic term, except magnetic fields do no work again, right? And the electromagnetic energy density is just this here. So it's the same as in the static case, in fact, which is, well, fascinating. Okay, and when I wipe out the blackboard, I'm going to show you an alternative derivation of this from the Maxwell equations directly. Are there any questions to the Poynting's theorem, by the way? All right. Now, starting from the Maxwell equations, which I hope I don't have to write up again, because you know them, we can show that the energy is conserved. The fact that energy is conserved is sort of baked directly into the Maxwell equations. So if you start out by the Faraday law, and also the Ampere's law, first of all, I rewrite this to have the time derivative terms on the same side of the equality sign. So the two of these become the following equations. Let's see. Now the first equation, I'm just going to multiply that by the electrical field on the left, taking the scalar product, and the H field on the bottom equation. And I guess you probably realize why now, because then I will get energy density terms here. Okay. So I multiply them, and then I add them together to get a new equation. And that looks the following way. We recall that this term is essentially the local energy density for the electrical fields, I mean. Equivalently for the magnetic fields is equal to and there's the work term, and these two terms that will become the Poynting's vector. So I just use the product rule again on that term. And this term I don't change because it's in the final answer anyway. And on the left, we recognize this as noted before. And I don't have to show you the trick again. It's essentially then the time derivative of the electrical field energy density and the magnetic one. All right, and now defining this as the Poynting's vector, and this is as the electromagnetic energy density, we get the Poynting's theorem again. And from this we see that, well, in the previous derivation we related the local density of energy and the flow of energy to each other, showing that this theorem is equivalent to showing the conservation of energy. And here we saw that this follows directly from the Maxwell equations. So energy conservation is built right into Maxwell equations from the beginning. And now I guess someone should have a question about energies or whatever. Yep. Sorry. It must be a miracle that I got it right in the end, right? Yeah, so you should start from the correct Maxwell equations when deriving something. Even if the end result turns out good, it's not a good thing. Okay, any others? Okay. And then before we move on to momentum conservation, which I'm sure you all expected by now, we have to take a small detour, and the detour will be into tensors. And we need tensors to, which is a mathematical concept, to get a hold of the physics in momentum conservation. So you'll have to excuse me for making this a math course temporarily, but if you don't know the math, then I think you'll be happy for learning it. Okay, as an example of tensors, we have seen the following. That is if you have an anisotropic material, which can occur, for example, in optical crystals. Let's say you have not a glass, which is amorphous, but a material which is translucent, but it's a crystal. Then you might have different dielectric properties along different axes because the atoms are aligned on a certain grid. And those might not coincide with the axis that you're working with, so to speak. So this gives you some sort of dependence on the direction you're heading, how the light propagates, for example, and how the D field behaves when you insert a certain E field in a material. And it's this dielectric tensor that relates these two properties in this case. It's still a linear material, but it's not isotropic, right? We've seen this before. So, again, I remind you that this is using the Einstein summation convention. So this is really equivalent to the following. As you can see again, each component of the E field can in principle contribute to the D field, meaning that the D field is not necessarily parallel to the E field. And I'm going to use the Einstein summation convention all the time from now on, so you better get used to it. So if you see two repeated indices, then there's a summation symbol in front. It's just that I don't bother writing it because there's always going to be one. Okay, and the notion of tensors is related to coordinate transforms in a way that we'll discuss in a short while. But loosely speaking, a tensor, yeah, yes, okay, but to define the order of the tensor first. I will loosely determine that as the number of indices required to write the tensor down. So in this case, the dielectric tensor is a rank 2 tensor because it has 2 indices, meaning that for each, well, the physics is pretty clear here, right? We have essentially a matrix of 9 elements which determine how each of the E field components affects each of the D field components. Right, and we will go through the properties of the scalars. And these are order 0. You all know these from before. And vectors. Which are order 1. For example, the electrical field is an order 1 tensor because I need 1 index to write it down. It has 3 components arranged in a linear fashion. And finally, we have higher order tensors. And these are ordered 2 or higher, as you might expect. And I think this is a good time again to encourage you to ask questions, especially if there's some sort of trouble with the indices, because you'll realize that I do some mistakes on the blackboard every now and then, and these will expand more or less exponentially when you have 3 or 4 indices. So try to stop me when if I make a mistake or if there's something that's not clear for you. Otherwise, you will just get confused. Well, I think we just take a break and then continue at 1:15.